Hello, AP Statistics. Welcome to Chapter 7, Part 2. In the last lesson, we introduced the sampling distribution for sample proportions. So what we're doing basically is we are taking a sample from a population. Now, the population does have a specific average to it, or a specific proportion. I used in class the proportion of Democrats in Indiana. I don't know what the proportion of Democrats in Indiana are, so I need to take a sample of people that live in Indiana, find out if they're Democrat or Republican, and I can find the proportion of Democrats in my sample, and then use that to extrapolate to the population. Extrapolate's maybe a bad word. It's make inference. Use the sample to make inference about the population. All right, we learned 3 rules about your samples. If you take a bunch of samples, in fact, if you take all possible samples and put them together, the average of the sample proportions will equal the true proportion. All right, so if your true proportion is here, you will get a nice cluster right around there. Now, some samples will come back larger than the true proportion. Like if this is 50%, some might come back as 60%. Some might come back as 70%. Some might come back as 40 or 30 or 20 or even 10%. There's variability in the samples, but we should cluster. Most of the samples should be right around what the true proportion is. The other rule, the second rule, is about the variability, is the spread. The spread. Sometimes you get really tightly clustered, sometimes you get more spread out. So this has to do with the spread. The spread or the standard deviation or the variability depends on the sample size, and it depends on what P is. So to minimize this, which is a good thing, we like to minimize our spread, or we like to minimize variability. 2 things we can do. Maximize this. All right, we want to make a big N, but not too big. In fact, it has to be less than 10%. For the standard deviation formula to be accurate, our sample size needs to be 10% or less of the population. So there is a upper limit to what N can be to be able to use this. But in general, if the larger N is, the smaller this is. That's how a denominator works. The larger this number is, the smaller the overall calculation is, and then the smaller this is, the smaller this will be as well. So how do I make this numerator small? Let's take a look here. If I do 0.5 times 0.5, that's as big as it gets. It's called the conservative value for P, because that's as large as we can make this numerator, 0.5 times 0.5. We could do 0.4 times 0.6, which is P times 1 minus P. And as you can see, that's not as big. We could do 0.3 times 0.7. We could do 0.05 times 0.95. That would work. You can see it's getting smaller and smaller and smaller. So the further that P is from 50%, the smaller this numerator gets, which implies the smaller this will be. All right, so to recap, how do I make this small? I make N big, or I make P far from 0.5. So you kind of gotta know that. And then 3, the sampling distributions will be approximately normal if N is large and P is not too near 0 or 1. Large counts condition. This is how you check that. If this is true and this is true, then you're approximately normal. So actually, we're gonna start this lesson by going to example 3, which was our warm-up for this class. All right, read through example 3. In a review of all criminal cases heard by Supreme Court cases in 11 states from 2000 to 2004, 391 of the 1,488 cases were decided in favor of the defendant. So we can get a proportion from that. 391 out of 1,488. Let P be the proportion of all cases reviewed that decided in favor of the defendant. What is the population parameter? So this is all court cases right here. So we can find a P. We can do 391 out of 1,488, which is 0.263. That's the true population proportion. All right, now a lot of times you don't know this number. A lot of times you're taking a sample to estimate this number. All right, so suppose that the proportion of 0.263 was not known. To estimate this proportion, you plan to select the sample and compute p hat, the sample proportion. The sample proportion that were decided in favor of the defendant. Okay, so if n equals 25, let's say our sample is 25, and this is what it is. What is the standard error of p hat? So now we can use the rule. This would be rule number 2. Before you use rule number 2, though, you have to check, is 25 less than 10% of 1488? And I believe it is. 1488 times 10% would be 148.8. So 25 is less than 148.8. So we are good to use the formula. This is rule number 2. So our standard error, standard deviation of the sampling proportion is this, which for us is just subtracting from 1, that's a 7, and we get 25, which is 0.088. All right. Now, if we change to 100, which is legal, we are good as long as we stay under 148. You gotta stay under 10% of the population. So 100 is within parameters. What is the standard error? So now let's change it. And now, you know what's gonna happen. We increased our sample size, which means we're increasing our denominator. So that's going to decrease this. It's gonna go down by something. We went from 25 to 100. So we quadrupled, we times 4 the sample size. Let's see what happens. So if I do 0.263 times 0.737 divided by 100, all right, and I calculate that out, I get 0.044. Now look at the results. By increasing the sample by a factor of 4, multiplying by 4, I decreased, so maybe think of it like this. This went up times 4. This went down times 2, divided by 2. By increasing by a factor 4, I halved my variability. It was 8% or 9% to roughly that. So, and that's what we expect, because this really is not a 100. This is the square root of 100. This is really 1 over 10 is what this is. And this is really 1 over 5. It's the square root of 25. This is 1 over 5 compared to 1 over 10, which is half, which makes sense because this is half of this. All right. So, how does the sample size affect the standard error of p? If n increases, let me write this out. If n increases by n, stop, don't write that down, by a factor of x. So if I double it, triple it, whatever, the standard error decreases by a factor of square root of x. If I went up 4, if my sample multiplied by 4, my variability decreased by 2. Same, if my sample multiplied by 9, my variability would decrease by 3. If my sample multiplied by 16, my variability would decrease by 4. X and root x. All right, now, suppose that n equals 25 and p equals 0.40. So now I'm changing, now what I'm gonna do is I'm gonna change my p. And I'm gonna get further from 50%, is what I'm gonna do. And we're gonna ask, how does p affect the standard error? So let's find out. Plug into my formula. we're going to do 0.4 times 0.6 all over 25, which is 0.098. And if I go down here, 0.05 times 0.95 over 25, I end up at 0.044. That's just coincidence that these two are the same. Don't look into that. But as we can see, what happened is if I go further from 0.5, okay, this is 10% away from 0.5, and this is 45% away from 0.5, you can see that the standard error went down. It's because that I'm making the numerator smaller, which makes this overall smaller. So how does P affect the standard error of P hat? You could say something like, as P increases distance from 0.5, the variability decreases. Now, P equals 0.5 is called the conservative value, not 0.05, but 0.5. P equals 0.5 is called the conservative value for P, because it will produce the largest numerator possible. 0.5 times 0.5 is 0.25. That's as big as you can get in this numerator. Does it surprise you that P hat tends to produce more precise estimates, which means you get less variability the farther the population proportion is from 0.05? It does surprise me a little bit. It seems like 50% is good, 50-50. But if you look at the formula just, it's right there. If you decrease this numerator, you decrease this. Decreasing the numerator decreases variability. Decreasing numerator means you're less spread out, which means more precise. So how do you decrease this? You have to make this far from 0.5. 0.5 and 0.5 is the largest this numerator can be. So does it surprise you? Kind of, but then when you look at the formula, not really. Finish the sentence: for a fixed sample, the standard error P hat is greatest when, so now we're talking greatest, how do we make the most variability? You want to make the largest numerator, so that means make P is close to 0.5, and we want a small denominator, and n is small. That's how you can get the largest standard error. Now, most of the time you don't want to get a great standard. You want to minimize, which means P is far from 0.5 and n is large, so it'd be the opposite. This question shows up all the time. How is the standard error affected? All right, example 1. Back to the lesson now. Suppose that 75% of young adults, internet users age 18 to 29, watch online videos. A polling organization contacts an SRS of 1,000 young adult internet users and calculates the proportion P hat in the sample who watch online videos. It says, identify the mean of the sampling distribution. Well, that's rule number 1. The mean of my samples will be equal to the true proportion. So therefore, the mean of my samples will be equal to P, which is 0.75. This would be, that's P in our problem. That's the known true proportion of young adult internet users aged 18 to 29. Yeah, I'm definitely not a young adult anymore. Makes me an old adult. B, calculate and interpret the standard deviation of the sampling distribution and check the 10% condition. Well, 10%, we're saying a polling contacts 1,000. Is 1,000 less than 10% of young adult internet users? I'm gonna say yes, even though I don't know 100% sure, but I'm pretty sure that 1,000 is less than 10%. So I'm going to 10%, check. Pretty good. Now we can do our standard deviation or standard error. If you'd like to call it that, you can call it standard error. P times 1 minus P over N. So that would be square root 0.75. You're going to be doing this calculation a lot. Okay, I believe calculates to that. All right, so now we have an average, we have a standard error. Let's check if it's normal. Is the sampling distribution p hat approximately normal? Check the large count condition. So we need to check NP and N times 1 minus P. Let's check it out. N is 1,000, P is 0.75, so this would be 750, and 750 is definitely greater than or equal to 10, so that one checks out. And now we do 1,000 times 0.25, which is 250, which is definitely greater than or equal to 10, so that one checks out. So therefore, we have a nice normal distribution. We have a normal distribution with an average of 0.75 and a sampling distribution of a standard error of 0.0137. So now what we can do is we can answer questions about this, such as this. Find the probability that the random sample of 1,000 will give a result within 2 percentage points of the true value. All right, so now to interpret that, we are looking that, let's call it, we're going to p hat, our sample proportion will be within 2 percentage points of the true value. So we need to be within, so I'm going to use less than or equal to, but it really doesn't matter. The equal doesn't really matter in continuous. I want to be within 0.73 and 0.77. That's within 2 percentage points of 0.75. All right, so now what I can do is, because it is normal, I can go ahead and make myself a normal distribution. And this normal distribution is centered around 0.75 and has a 0.0137 standard deviation. Okay. And I want to be within 0.73 and 0.77. Now I'm going to use norm CDF with a lower bound 0.73, upper bound 0.77, average 0.75, standard deviation 0.0137. I'm going to plug that into my calculator, and out pops the area, and it's about 85.8556. Hopefully you know how to do that in your calculator. So what this means is about, in general, if I do a bunch of samples, 85.56% of all of my samples should be within 2 percentage points of 0.75 of the true proportion, plus or minus 2 percentage points of that. So it's nice to know. If the sample size were 9,000 rather than 1,000, so the sample size went up by a factor of, it went up, N went up by a factor of 9. There, N went up by a factor of 9. So therefore the standard error will go down by a factor of root 9, or by 3. That's what's going to happen. All right, we did that in the warm-up. We talked about that. If your sample size goes up, if your denominator increases by x, the variability will decrease by root x. So if we go up by 9, the variability will go down by 3. And we're going to be more tightly clustered. This is going to give us tighter clusters than this. It'll be the difference between this for like 1,000 maybe, and this for like 9,000. It's just going to be more tightly clustered together. We're going to have less variability. We're going to have 3 times less variability. That's what we end up having. Is 9,000 legal? Can we do it? Is 9,000 less than 10%? of all young adult internet users ages 18 to 29? I still think yes. I still think 9,000 would work. Okay. Next, we're going to talk about good estimator of a population. Now, the goal is to get samples that would estimate the population. Right? So let's say that the percent of Democrats, the proportion of Democrats in Indiana is 50%. It's 50-50, Republican, Democrat. I take a sample, and my sample comes back as 80% Democrat. I take another sample, comes back 80%. And I keep getting an overestimate of the true proportion. That's called a biased estimator. So, in general, we want to choose a statistic that is unbiased. A statistic with a sampling distribution that is centered at the actual value of the population characteristic is an unbiased estimator. In other words, a statistic that does not consistently tend to underestimate or overestimate the value of a population characteristic is an unbiased estimator. We like unbiased estimators. We don't like bias at all. State biased or unbiased. Now this, you can see Mounds here, which is different from here. So this one would be biased. There's something going on here which is making my samples systematically overestimate the true value. This one is unbiased. It's lining up pretty nicely. And this one is also unbiased. Now comparing these two, this one's better. This one's more tightly clustered. This one has less variability. This one's a little bit more spread out. If I had to pick one of these, I would pick this one. This is the best one. 2, choose a statistic with a small standard error. Standard deviation of a sampling distribution is called standard error. A statistic that is unbiased has a small standard error is likely to result in a it's likely to result in an estimate that is close to the actual value of that population characteristic. If a sampling distribution is centered very close to the actual value of the population characteristic, small standard error ensures that the values of the statistic will cluster tightly around the actual value of the population characteristic. Okay, here's the standard error. Talked about that. State if the estimate is biased or unbiased. These are both unbiased. Why did I repeat this? I just did this. These are both unbiased. And this one is more spread out than this one. This one has less variability. This one, the standard deviation will be smaller than this one. I don't know why I repeated that. Sorry. All right, last little example here. In the histogram on the left shows the interval in minutes between eruptions of Old Faithful Geyser for all 222 recorded eruptions during a particular month. 222 in a month. All right, for this population, the median is 75 minutes. So on my graph, that would be right here. There's 75 right there. Okay, and 75 right here. Good, no? Now, this is a weird question because it's using median instead of means, or it's using a median instead of a proportion. And we don't really deal with medians all that much. So this would actually be like a question number 6 on your FRQs. If you remember, number 6 on your FRQs is called the exploration. And that is going to involve something that we don't cover in this class. Like, if you look in your formula packet, there's no formulas for medians. That doesn't mean you can't apply what we learned to it. So that's what the exploration is. Number 6 is like applying what we learned in class to something that's probably going to be new. So this is a good example, using medians instead of proportions. We're looking at the true median, and there's no notation for a median. We use technology to take 500 SRSs of size 10. So this represents 500 samples of size 10. The 500 values of the sample medians are displayed in the histogram on the right. The mean of these 500 values is 73. the mean was 73.5. So the mean's actually a little bit over, a little bit. Is the sample median an unbiased estimator? It's close. All right, they're close, but technically the median is not right on top of the mean. So I'm actually gonna say no. If we're doing 500 samples, they should be right on top of each other. These should be right on top of each other. No. 75 does not equal 73.5. All right, so this is the true value, and this was the true value. This was the true median. This was the average of the medians. So they didn't line up. So we're gonna say no. You gotta line up. All right, suppose we had taken a sample of 20 instead of a size 10. Now this is always gonna be a good idea. Increase your sample size. As long as it's less than 10%, which 222, 10% would be 22.2. So we are under 222, 10% of 222, so we're good. Would the variability in sampling distribution of the sample median be larger, smaller, or about the same? It would be smaller. It will always, increasing the sample size will always decrease the variability. The variability will definitely be smaller. Again, increase in sample size, as long as you stay under 10%, will always decrease the variability. Describe the shape of the sampling distribution of the sample median. We can use socks here. So which one am I doing? Describe the shape of the sampling distribution of the sample median. Simulated sample median. All right. If I'm just looking at this graph right here, it is bimodal. You got a peak here, you got a peak here. It has a peak at between 80 and 85. It has a peak between 50 and 55. With a 50 and 55 happening around 28-ish, and this peak happening around, I don't know, 48-ish. That's shape. Bimodal would be good. You say double peaked if you would like to say that instead. We would say, let's see here, outliers. Doesn't look like there's any outliers. There's no gaps. Run through socks. What's next? Center. The center of the graph, it tells us the mean of these 500 values was 73.5, so we could use that as the center of the graph. And as far as the spread of this, I would probably do range. And now to do range, you need a minimum range. So the minimum range is here to here. So it would be 95 minus 45. Should be 95 minus 45. It's 50. I don't know why I did that in my calculator. So it has a minimum range of 50, but it could also have a range of here to here. That would be 100 to 40, so 60. The range is anywhere between 50 and 60. You have to do that because we don't know where exactly these values fall in that interval. So the range is between 50 and 60. All right, that's the lesson. Big part of the lesson, though, is understanding these three rules for sampling distributions. It's all about samples making inference now. Bye-bye.